Hi, this is Rick Kolk, and today we're going to talk about the VisSim embedded fixed point block set. We will cover the description and use of the fixed point blocks, configurations, and features that allow any algorithm to be designed and simulated in fixed point prior to code generation and execution on the embedded platform. The fixed point block set is located under the Blocks menu in the submenu Fixed Point. As with all VisSim menu items, you may use the VisSim menu bar or the tree-structured menu and browser window located to the left of the workspace to access these blocks. The block set contains over 30 blocks ranging from arithmetic and booleans to controllers and filters. Practically any algorithm can be represented using the fixed point block set. All fixed point blocks have standard properties that apply to the output signal of the block. We'll look at the constant block to describe these properties. I'll place one on the screen, right-click to open the Properties window. The radix point is analogous to the decimal point in a base 10 number. The bits before the radix point represent the integer part of the number, while the bits to the right represent the fractional part. The word size is the total number of bits in the fixed point number. It is normally set based on the target architecture. Precision is the smallest difference between two consecutive discrete values. It can be calculated as the smallest discrete value using the radix point and word size. For example, 4.16 format has 12 bits to the right of the radix, so the precision is equal to 2 raised to the minus 12. Similarly, 16.16 format has 0 bits to the right of the radix. The precision is equal to 2 raised to the 0 power, or 1. Fixed point targets only recognize integer values. VisSim embedded CodeGen automatically converts decimal numbers to scaled integer values by dividing them by the precision. For example, the constant 3.12 in format 4.16 is represented as a scaled integer equal to 3.12 divided by the precision equal to 2 raised to the minus 12, giving a result of 12779. The representable range presents the range of values that can be represented with the radix point and word size selected. This is a read-only field. The constant value is the value of the constant, and it may be entered as a floating point value. The auto-scale checkbox is used during simulation. When checked, auto-scale will alter the radix point such that the block output time history lies within the representable range during the entire simulation. An overflow error occurs during the simulation when a block output value exceeds the representable range. The Warn on Overflow checkbox activates a warning dialog that appears when an overflow error occurs. You must also activate the Enable Overflow Alert messages in the dialog box for the fixed point block set configure command. We'll cover this next. The min value seen and max value seen display the high and low watermarks of values that come through the block. These are read-only fields. The fixed point block set configuration command, located under Tools, Fixed point block set configure, is used to set global conditions on all fixed point blocks used in a model. The Override Word Size checkbox overrides the local word size in all fixed point blocks in the model, with the word size value shown in the drop-down menu. The word size dropdown is only used when the override word size is checked. The Enable Auto-Scaling checkbox turns on auto-scaling for all fixed point blocks in the model that have their auto-scale option checked. The Reset Radix Point at Sim Start checkbox resets the radix point in all fixed point blocks in the model to 0 at the start of a simulation. This option is used in conjunction with the auto scale option in each fixed point block during simulation to automatically identify the radix point value that produces precision without overflow. The Enable Overflow Alert Message checkbox turns on the overflow alert messages for all fixed point blocks whose auto-scale option is checked. To view the automatic commenting and efficient execution features of VisSim Embedded Fixed Point Code Gen, we'll illustrate code gen for a simple model using a host target. We'll construct the model using two constant blocks, a gain block, and two display blocks. I will configure the gain to have a gain of 2 with a format of 6.16. I will configure the second constant block to have a gain of minus 2.81 with a radix point located at 8. Connect these together, and we will generate code. So under the Tools Code Gen window, I will select my target as host, generate code, and view the code. Now the code is brought up in Notepad. A couple things to notice. T4 is the output of the times 2 multiply. You'll notice the inline shifting. You'll notice the 1 has been transformed to a scaled integer equal to 4096 due to our 4.16 formatting. And you'll also notice the comment that retains the original value of the gain and the original value of the constant. T3 is the constant value being sent to the second display block. In scaled integer, this is equal to minus 719, and the comment indicates it is the minus 2.81 at the 8.16 format. This example illustrates overflow messaging and display of the min value seen and max value seen in a fixed point gain block during simulation of a model. Our model consists of a slider, a fixed point gain, and display block. The slider is configured to range from minus 100 to 100. The fixed point gain block is configured with a gain of 5.5. And we will select Warn on Overflow and take the default radix point setting of 4. Our simulation will be set to run in real time for 10 seconds in increments of 10 milliseconds. In the Tools Fixed Point Block Set Configuration menu, we will enable overflow alert messages. Running the simulation and adjusting the slider, we see the VisSim overflow message, which I will ignore, and continue to adjust the slider between its min and max values for the duration of the simulation. After the simulation has completed, opening the gain block reveals the min value seen and max value seen to be minus 550 and plus 550, which makes sense because we had varied the slider between minus 100 and plus 100. The min value seen and max value seen information can be used to adjust the radix point to a value that prevents overflow before code is generated and executed on the target. This example illustrates the VisSim auto-scaling feature. For each fixed point block, VisSim maximizes precision by selecting the smallest acceptable range for each fixed point block in a model, such that overflows do not occur. A model consisting of a sawtooth signal taken from the block's signal producer menu is connected to one input of a fixed point sum block. The other input is connected to a fixed point constant block, which provides an offset to the sawtooth signal. The difference is applied to a fixed point gain block, and the result is presented in a display block. The sawtooth is set to an amplitude of 200 and a frequency of 1 Hz. The constant block is set to a value of 100 using 4:16 format, and the auto-scale checkbox is checked. The sum is configured using 4.16 format, auto-scale checkbox checked, 2 inputs, the top input being positive, the lower input being minus. The gain block is set to a value of 5.5 using 4.16 format, again with the auto scale option checked. In the fixed point block set configuration, under Tools, we will enable auto scaling. The simulation is executed by clicking Go. The constant, sum, and gain blocks have turned red, indicating that each has undergone an overflow. The results of the VisSim Autoscale feature, showing the format that prevents overflow, are displayed on each block. In the constant block, VisSim has calculated an 8.16 format, for the add block an 8.16 format, and for the gain block a 16.16 format. If I accept these changes and rerun the simulation, the new formats confirm that they do not result in an overflow. This example illustrates percent CPU savings potential of a digital filter implemented in fixed point rather than floating point. C code is generated and executed on a Texas Instrument F28069M launchpad. Filter response and percent CPU utilization are displayed. A source model is created consisting of two identical second-order filters. The filters are created using the transfer function block located under Blocks, Linear System. Both filters are executed at a 0.1 millisecond update time, and both filters receive input from the same analog input channel, ADC0. One filter is implemented in floating point, the other in fixed point, with format 8.32. This is the floating point implementation. We look at the properties of the transfer function and see the discrete update time is set to 0.0001. The digital filter is implemented identically. However, we select the Use Scaled Fixed Point and specify the 8.32 format. Each filter is implemented in a triggered compound block. This allows us to observe the response of either filter. Setting the button to float will cause only the floating point filter to execute. Setting it to fixed point will cause only the fixed point filter to execute. With the source model developed, we will create code by selecting the compound block and generating code under the Tools menu, selecting the target, F280X, and including the VisSim communication interface. At this point, we're ready to move to the debug model. The debug model consists of a target interface block configured with the C code generated by the source model. The sample rate is set to 10 kHz, and the Show CPU Utilization checkbox is checked. The debug model is configured to run for 10 seconds in real time with auto restart and retain state selected. After connecting the F28069M launchpad to the computer, the debug model will be executed. The upper plot displays the floating point and fixed point filter responses. The lower plot displays the percent CPU utilization. While the model is running, the button controlling the filter is clicked. From the upper plot, it's seen that both filter responses are nearly identical. There will be some degradation in the fixed point filter. However, this can be influenced by selection of the radix point. In the lower plot, we see the percent CPU utilization is almost a factor of 10 times larger for the floating point filter. 1.8% utilization for the fixed point versus 16.76 for the floating point filter. So in summary, when a target does not support hardware multiplier divide, the operations must be performed in software. A software divide is approximately 100 times slower than a hardware multiply. Similarly, a software square root involving several divide operations is between 200 and 300 times slower than a hardware multiply. Using fixed-point arithmetic greatly reduces the CPU utilization required for software multiplies, divides, and other complex operations. In the digital filter example, we saw almost a factor of 10 times savings in the % CPU utilization. Thank you.